Bismillahirrahmanirrahim. This video is linked with my previous video about linear transformations. And in this video, I will answer some of your questions. So the question was, is it always very easy to find the counterexample to prove a transformation is not linear? So once again, if we see that when a transformation is linear, if it preserves vector addition, it preserves scalar multiplication, and it maps zero vector into the zero vector. So actually there are two conditions, the condition number 1 and 2, and the third condition can be easily verified by using conditions 1 and 2. But this third condition is very beneficial when we prove that the transformation is not linear. Now, to answer the question, I must say that there may be some tricks to identify that which one of the property fails. So if that trick works, you may easily come up with the counterexample. Otherwise, if you cannot find such trick in your particular problem, then you may try to disprove it by taking general vectors and proving that vector addition or scalar multiplication does not hold in that case in general. So let's try out in the examples. So again, the same example that we did in the previous video. So if you see in this video that this factor, this product factor cause the multiplication effect, this factor, if you see this factor, then if this coordinate has multiplying factor, or you can say that I may write here, if any of the coordinate has multiplying factor, so naturally it cannot be broken into parts addition wise. So in this case, you may find out that vector addition may not preserved. So you can take any example like we did in the previous video, and any example and it will work in this case. Otherwise, you may take any general vector. You may take let v1 and v2 be any two general vectors in R2. And in this case, you calculate their sum v1 plus v2, x1 plus x2, and y1 plus y2. And if you apply T1 on this sum, then you see that this will becomes x1 plus x2 times y1 plus y2 and x1 plus x2, and this comes out to be x1 y1 plus x1 y2 plus x2 y1 plus x2 y2. And you will see that if we add these images, then these images will become x1 y1 x1 plus x2 y2 x2 and it becomes x1 y1 plus x2 y2 and x1 plus x2. So you note that these two are not equal, and again you claim that the vector addition is not preserved here. So again you see that this factor cause problem, this factor cause problem. So this, due to this factor, the addition preservation rule does not imply here. Similarly, the next trick may be about the translational effect. So if you see here, if you see here, then the constant is added in a coordinate. So it will cause a translational effect in the transformation. And you know that when a transformation has a translational effect, then it will cause problem in mapping 0 into 0 vector. Here you can also see that vector addition will also not preserve here, and like we did in the previous example, you may take a general vector and you may show that the vector addition, for example, does not preserve here. So again, if we talk about the next trick, then you see that over here, the use of absolute sign. So the use of absolute sign in somewhere, the use of will affect the presence of negative sign. So this points out that the scalar multiplication may not hold, especially if we multiply with a negative number. So that is why if we take any scalar that is negative, for example, if we took in that example k is equals to -2, then this you can easily counter that this transformation is not a linear transformation. You can also have a look that due to this absolute value, the addition vector addition is not also not preserved. If you take two numbers that are negative in the x component and you take the difference of them, then the absolute value is not equal to the sum of the individual values. And so you can also use this fact to prove that the transformation is not a linear transformation. Lastly, I want to make it clear that the mapping zero vector into a zero vector does not always imply that the transformation is linear. For example, you see this transformation T3, it always maps zero vector onto the zero vector. But this is not a linear transformation. So this property of mapping zero vector into the zero vector, we cannot use this property to prove that the transformation is linear. But this property is usually beneficial in disproving the linearity. That is, if the transformation is not a linear transformation, then it does not maps 0 into the 0 vector. Or you can say that if a transformation does not mapping 0 into the 0 vector, then it will no more a linear transformation. So thank you for your attention. That's all in this video.